Intro. Have you ever looked up at the night sky and felt a sense of profound wonder, a feeling of being infinitesimally small, yet inextricably connected to the vast cosmic ocean? For millennia, we stared into that darkness with only our eyes and our imagination. We told stories, charted constellations, and built mythologies to explain the lights above. But there came a time when we were no longer content to just look. We wanted to reach out, to touch, to measure, to understand. We built machines born of human curiosity and sent them into the void to answer our oldest questions. Faint whispers of data crossed billions of miles and tore up our textbooks. Today, 5 pivotal experiments that rewrote the story of the universe and our place within it. So buckle up. The cosmos is waiting. Imagine pointing our most powerful telescope at a patch of sky that looks utterly empty, a grain of sand held at arm's length near the Big Dipper. This wasn't just any patch of sky, it was a region meticulously chosen for its apparent void, a place devoid of bright stars or known celestial objects. The goal was to stare into the deepest, quietest corner of the universe we could find. For 10 consecutive days in December 1995, astronomers devoted 100 hours of precious telescope time to that profound darkness. Many in the scientific community called it an outrageous gamble, a potential waste of a priceless asset. What if, after all that time, the image came back blank? It was a shot in the dark, in the most literal sense. Undeterred, Hubble opened its eye. Over 342 separate exposures, it patiently gathered every single photon it could from that minuscule window. Each exposure was like a single brushstroke. The final masterpiece would only be revealed when they were all digitally stacked together, a process designed to cancel out noise and build up the faintest signals from the edge of the cosmos. When the final composite image was processed and released, the skeptics went silent. The frame wasn't empty, it was breathtakingly, overwhelmingly full. Each smudge, each swirl of color, wasn't a star. It was an entire galaxy. Over 3,000 of them were captured in that one sand grain of sky. There were majestic spirals, glowing ellipticals, and chaotic irregulars, even distorted mergers caught in gravitational dances, each containing hundreds of billions of their own stars. We weren't just looking across space, but back through time. The light from the most distant galaxies had traveled for billions of years to reach Hubble's mirror. The faintest, reddest smudges were infant galaxies, seen as they were when the universe was just a fraction of its current age. This redshift is the cosmic equivalent of a Doppler effect for light, stretching it to redder wavelengths as the universe expands. The Hubble Deep Field was a core sample of cosmic history, all in one frame. It shattered old estimates of the universe's population and forced a new cosmic census. Extrapolating from this tiny patch to the entire sky, astronomers now estimate there are not millions, not billions, but perhaps 2 trillion galaxies in the observable universe. This single observation pivoted the entire field of cosmology, providing clear, direct evidence of how galaxies evolve over time. And it was just the beginning. Inspired by its success, astronomers pushed even further with the Hubble Ultra Deep Field and the Extreme Deep Field, peering even deeper into the dawn of time. Each new image found more galaxies, more complexity, and more history, rewriting our place among the stars. In the summer of 1977, humanity launched 2 remarkable emissaries into the cosmic ocean, Voyager 1 and Voyager 2. These weren't just probes, they were time capsules, carrying the sights and sounds of Earth on golden records, destined for any civilization that might one day find them. Their initial mission was made possible by a celestial coincidence, a planetary alignment that happens only once every 176 years. This rare configuration enabled a grand tour, a gravity-assisted slingshot maneuver that would bend their paths from one gas giant to the next. They swept past the turbulent clouds of Jupiter, the majestic rings of Saturn, the tilted axis of Uranus, and the wind-swept plains of Neptune. But after rewriting the textbooks on our own solar system, their journey was far from over. They just kept going. Before venturing too far, at the request of astronomer Carl Sagan, Voyager 1 turned its camera around one last time. From 6 billion kilometers away, it captured an image of Earth as a single, tiny pixel suspended in a sunbeam, the iconic pale blue dot, a humbling portrait of our place in the cosmos. Powered by the steady decay of plutonium, their instruments were designed to last. But no one imagined they would keep working for this long, sending back data year after year, decade after decade. Their new goal was audacious: to find the edge of the sun's magnetic bubble, the heliosphere, and taste the space between the stars. In August 2012, Voyager 1's instruments detected a dramatic shift. The solar particles that had surrounded it for 35 years suddenly plunged, while high-energy galactic cosmic rays surged. It had crossed the heliopause, the invisible boundary separating our solar system from the vast expanse beyond. It became the first human-made object to enter interstellar space. Voyager 2, on a different trajectory, followed its twin in 2018, confirming and extending the incredible discovery. Because its plasma instrument was still working, it could directly measure the density and temperature of the interstellar medium, revealing a cosmic shoreline that was far more complex, churning, and dynamic than anyone had predicted. It even detected the faint hum of interstellar plasma waves, the very vibrations of the space between stars. These marvels of engineering run on computers with less processing power than a modern car key fob, yet they endure the harsh radiation of deep space. To extend their lives, engineers on Earth perform a kind of remote control surgery, carefully shutting down non-essential systems and rerouting precious power. Decades on, these silent sentinels still measure and report from a place no human has ever been, their faint whispers traveling for over 22 hours to reach us. They are our first true interstellar explorers, rewriting our map of the sun's domain and our understanding of our home in the universe. On July 20, 1969, Apollo astronauts left a small panel of prisms on the moon, a retroreflector array. Each corner cube prism bounces light straight back, no matter the incoming angle. On Earth, observatories fire short, powerful laser pulses at the array. Photons take about 1.25 seconds each way, time the round trip and, with light speed, calculate Earth-Moon distance. Picosecond timing yields millimeter accuracy, hair-thin precision over continental scales. For over half a century, this data has rewritten the Earth-Moon story. The moon spirals away at about 3.8 centimeters per year. Fingernail growth speed, a result of tidal interactions with Earth. Subtle orbital wobbles hint at a partially liquid lunar core. Most importantly, it stress tests general relativity in the Earth-Moon laboratory. If Earth and Moon fell differently due to composition, we'd see it, but we don't. Decades of ranging show no deviation. Einstein, so far, is right. For 3.8 billion years, life evolved under gravity. On the ISS, we take it away. In microgravity, station and crew are in constant freefall, an orbiting laboratory. Here we study physics and biology in ways impossible on Earth. Protein crystallization thrives in space. Slow, ordered growth, without gravity's disturbances. ISS crystals are larger, more uniform, higher quality. Sharper structures open paths for drugs targeting cancer and muscular dystrophy. Some bacteria, like Salmonella, become more virulent in space. Meanwhile, the human immune system appears suppressed, vital for long-duration flight and medicine. With convection muted, we isolate diffusion and surface tension. Flames turn spherical, insights that improve combustion and reduce pollution. Fluid behavior in microgravity informs fuel tanks and life support systems. We're gravity chauvinists by habit. Space Force is a new lens. 250 miles up, textbooks in biology, medicine, and materials are being rewritten. Comets are icy, dusty time capsules, ghosts from the solar system's dawn, preserved in the deep freeze of space for over 4.5 billion years. These primordial bodies hold clues not just to how our solar system formed, but potentially to the origins of life itself. To unlock these secrets, humanity embarked on one of its most audacious missions, to chase down a comet and land on its surface. Europe's Rosetta spacecraft launched in 2004 on a 10-year odyssey. Its journey was a masterpiece of celestial mechanics, involving multiple gravity-assist flybys of Earth and Mars to build up enough speed to intercept its fast-moving target. That target was Comet 67P Churyumov-Gerasimenko, a strange dual-lobed world of ice and rock, tumbling through space at over 135,000 kilometers per hour. In 2014, Rosetta became the first spacecraft to orbit a comet. Its cameras revealed a breathtakingly alien landscape of sheer cliffs, dusty plains, and deep, circular pits. These pits, scientists realized, were active sinkholes, formed as subsurface ice turned directly into gas, causing the ground above to collapse. This process also powered the dramatic jets of gas and dust that erupted from the comet's surface as it neared the sun. But orbiting wasn't enough. The mission's climax was to land. Then came Philae, a 7-hour nail-biting drop to make history. The landing was chaotic. Anchoring harpoons misfired on contact with the unexpectedly hard surface. The tiny lander bounced, not once, but twice, traveling over a kilometer before finally settling in the permanent shadow of a cliff. Its solar panels were starved of light, but its primary battery was full. In 60 precious hours, 10 instruments got to work. It drilled into the surface, took thermal and magnetic measurements, and sniffed the thin atmosphere for exotic gases. The results were astounding. Philae detected 16 complex organic molecules, some never before seen on a comet, including the amino acid building block glycine. This strengthened the idea that comets can deliver life's chemical precursors. While this isn't evidence of life itself, it confirms that the raw ingredients for it are common throughout the cosmos. But 67P's water told a different story. Its unique isotopic signature didn't match Earth's, suggesting that asteroids, not comets of this type, were the primary source for most of our planet's oceans. Long after Philae fell silent, Rosetta continued its vigil, mapping, measuring, and watching a living comet breathe as it rounded the sun. To know our origins, we landed on a speeding bullet of ice and dust, and listened to the whispers of our own cosmic past. From a million-second stare into the void to a gentle landing on a comet, each experiment is a triumph of curiosity. They are stories of ingenuity, perseverance, and our unyielding desire to know. We sent our proxies to see, to measure, to touch, to taste. In return, the universe proved more complex, more surprising, more magnificent than we imagined. Science is a story constantly rewritten. Each answer opens a dozen new questions. Galaxies teem. How did they form? We crossed into interstellar space. What lies beyond? Microgravity reveals life's secrets. How will we adapt to other worlds? As long as we ask big questions and build bold tools, we will explore. Because when we study the cosmos, from proteins to superclusters, we are learning the story of ourselves. We are, after all, a way for the cosmos to know itself.